Hey guys, so today I'm going to be discussing my semester specialization, and that's going to be centered around soil remediation for nuclear waste contaminated soils. So I hope you guys enjoy. Thanks. Okay, so the main question my report in this presentation aims to answer is how do we actually effectively clean soil if it's been contaminated with something such as radioactive waste? Keeping that in mind, some useful background information about my actual report should probably be stated just to get a grasp on some of the conceptual items and preliminary information that might be necessary later on in the presentation. For this report, the main contaminant that will be referenced often is highly radioactive waste, otherwise known as mixed transuranic waste. So this groups many individual elements into one classification, which is what is often seen at contaminated sites. It's really rare that these occurrences of individual elemental contaminations happen, so this just helps with ease of classifications and references. There are a number of ways these contaminants enter the ground as well, such as simply being dissolved in groundwater, for example, or maybe in more chemically based ways, such as precipitating out of a solution after some time. It's important to know what these mechanisms are because more often than not, it's the very same physical chemistry engineers take advantage of to actually remove them. And finally, there are many unique methods that have been developed to effectively remediate all different types of contaminants, and some are quite interesting. It gets very difficult, however, when the contaminant is a nuclear inorganic because these don't tend to play by the same rules as chemical rules as one may say, like with other compounds such as oil or natural gas. But nonetheless, most examples can be divided up into main categories such as extraction or the physical removal of the contaminant, mobilizing, which doesn't actually remove it, but it just prevents it from spreading, it's still in the ground, and finally destruction, which destroys it in situ, but it probably leaves some residue behind. So those are just some of the main useful background information you should probably keep in mind. So this is just a figure. I thought it was really neat because it's color coded, so it gives you an idea of where these contaminants are on the periodic table. So we're essentially dealing with the last row, bottom row, the highly radioactive stuff, the reds, the purples, some of the oranges in there too. But that's essentially what we'll be dealing with, and that's just graphically displayed over the periodic table of elements. So here are some examples and common remediation methods that are currently being employed today. They basically can all be divided up into physical or chemical categories, which means they either remove the contaminant physically by physical means or by a chemical reaction or chemical means. All of these remediation methods must consider a cost-benefit analysis. Something like acid washing may remove all acid-soluble substances, but you're leaving behind the acid and residue and hazardous waste products, and that may create more harm than good. So that's just something all remediation methods in general have to consider. And the main takeaway from this actually is the most common method used today is something called in situ grouting. That's due to its really low cost, its minimal byproducts, and its very simple deployment. And we'll expand more on that throughout the presentation. So this just expands on what was previously mentioned before. Of course, you have the monetary cost, you have environmental aspects like byproducts some of these methods produce, and of course the availability and other hazards that, surrounding the actual technology itself. And all three of these things go into choosing which method to use. So in my report, I considered a case study conducted at Oak Ridge National Laboratory. It was an experiment that involved stabilizing a trench that was contaminated with MTRU, and it used in situ grouting as the technology. And the experiment basically had two main goals. It wanted to minimize the leachate migration or the groundwater flow below the trench, which possibly could spread the contaminants, and it wanted to maximize the trench stabilization or the compressive strength of the soil. And interestingly enough, it actually used PCC, Portland concrete cement, as the physical grout that was injected. So after the experiment was conducted, some of the results are highlighted here. It definitely increased the soil stability through a standard penetration test. It required greater than 100 blows to reach 1 foot of penetration. So it's very stable. It should be since it's concrete. And it still had somewhat of a high hydraulic conductivity going past it. And so in the future, they plan to expand with different kinds of particulate grouts, such as finer ones like clays and silts and synthetic microfine particles to possibly diminish that hydraulic conductivity. So just as in situ grouting involved injecting particulate matter into the ground to effectively surround and trap contaminants in the ground forever, I also considered supercritical fluid extraction another remediation method in my report because it had a unique characteristic to it, which actually was the ability to remove nuclear inorganics from the ground, specifically a report published by BNFL for removing plutonium and americanium from soil. And this is done by injecting extremely compressed fluids and gases to extract contaminants by forcing them out and actually causing some dissolution due to the extreme environment that they would be surrounded in. It's relatively new for the nuclear contaminants and nuclear world, but it does have proven success with remediating petroleum contaminants up to 150 tons per day, which is fantastic. So they saw this and they adapted it appropriately for nuclear inorganic removal, which essentially just they needed a different type of supercritical fluid or gas to use. They specifically chose CO2 due to its chemical properties to effectively dissolve nuclear inorganics. But that was really the only change, and it showed some success. Just shows a really simple schematic on how this method would work. You would have CO2 as a gas being chilled to make it a liquid. It would be pumped under extremely high pressures into some sort of extraction vessel, which contaminated soil could be loaded into. The contaminants would flow up through a back pressure regulator, which would bring it back to normal pressures, and then the sample would be collected in concentrate. So overall, the results proved very promising for using this method as a means of removing nuclear inorganics. Three separate scenarios and conditions were considered. A maximum amount of plutonium and americanium of 80% and 93% were removed in one scenario, and even a minimum amount of 43% plutonium and 60% americanium was removed in another scenario, which is still fantastic and pretty much unheard of in today's times. So it could be considered an extremely effective solution at remediating nuclear inorganics, something really not possible. There's just one more remediation method my report considered. It was called multi-phase extraction remediation. It's a newer approach. It's very similar to SFE, but instead of injecting something under high pressure, it uses strong suction to remove all different phase states of contaminants, such as physical ones, liquid ones, and even gaseous ones, all at once. And then, of course, further separation to individual phase states of contaminants would commence once they were out of the ground. And it's really important for the natural gas and oil energy sectors because they constitute even a larger percentage of energy production than nuclear does. So it provides some remediation methods for them as well. And it also does have proven success working in the nuclear scope as well. And I just thought it was pretty interesting to show. So this just shows a really simple schematic for multi-phase extraction and the typical configuration of it. You'd have something in the ground sucking up gaseous contaminants, liquid ones, and even physical ones. It would bring it to the surface into some sort of separator, which would separate the liquids from the gaseous ones, and they would all go to their own respective treatments. Some of the conclusions and main takeaways I hope to provide people with this presentation and my report are first, SFE shows promising results with remediating soils contaminated with MTRU and other nuclear inorganics. However, in situ grouting still remains the most used method just because its simplicity, its low cost, and its easy deployment. But we're still not getting that true removal of contaminants, which we really want to start accepting now. So if cost optimization does happen for SFE in the future, we should start to see that take over in situ grouting as the most common remediation method. Yeah, we're making progress removing notoriously unmanageable nuclear inorganics, And finally, all this is to provide realistic and effective remediation methods, which hopefully diminish the negative connotations associated with nuclear energy because it's such a fantastic form of it. It produces no greenhouse gases, it's extremely efficient, and if we have a method, a proven method, that will remediate possible contaminants, then it will hopefully make it a more widely used energy. There are some additional references for future readings, and thank you guys for listening.